morning, everybody. My name is Francesco Conti, and I'm here to present PULP, an OpenRISC-based ultra-low power parallel platform on behalf of the whole PULP collaboration. First of all, let's give some motivation to our work. One of the big buzzwords in the current world of tech is that of the Internet of Things. What the Internet of Things is really about is about smart sensors. Smart sensors are nodes, devices, that must be able to do three different tasks. The first is, of course, sensing, which is usually performed using very low power or ultra low power sensors such as MEMS, ultra low power imagers, and so on. This task can be performed within a power budget of about up to 2 milliwatts and down to 100 microwatts. Second task is analyzing and classifying the data coming out from the sensors. This is usually performed right now in the state of the art using low power microcontrollers, typically using the ARM Cortex-M series MCUs or similar. This kind of devices can work within a power budget of up to 10 milliwatts and can deliver up to about 25 mega operations per second of performance. The third task is that of transmitting the output of our classification work to the outside world. This is usually done using very short range, medium bandwidth, and very low rate transmitters. Or in the case of software updates and new commands for the sensor node, we use long range, very low bandwidth transmitters. In any case, we want to keep the radio idle as much as possible to keep the power consumption low, as the active power consumption of such devices can be up to 15 milliwatts. That said, this kind of tasks can be performed within a system in a few milliwatts of power envelope. So we can power such a system with a small battery, a supercapacitor, or a combination of these with power harvesting from the environment itself. Our question now is, can we do more than what is available in the analyze and classification stage? Is it possible to perform more complex tasks? Well, not with 25 mega operations per second of available performance. That is impossible, unfortunately. However, we believe it is possible to substitute this stage with something more complex, with something which is much more energy efficient than a typical microcontroller. And we believe that the solution to this problem is given by ultra-low power parallel processing. By using parallel processing at near threshold voltages, we can achieve up to 2 gigaohms of performance within the same 10 milliwatts total power envelope. Okay, so as I said, I talked about gigaohms at about 1 to 10 milliwatts of power envelope. So this translates to a number which can be resumed in 1 to 10 picojoules for every operation which is performed by our computing platform. This is traditionally the target of ASICs combined with microcontrollers. However, we want our platform to be much more flexible than that. An ASIC has non-recurrent engineering costs which are way too high for the typical sensor nodes we may want to put in an IoT node. So what we thought is of building an entire technological stack starting from low power silicon, the best in class low power silicon available, and using open source processors and RLIPs, open source compilers and tool chains, up to the virtualization and programming model layers, in such a way that we can build a parallel, programmable, and heterogeneous platform for ultra-low power computing. How to do this? The trick is share. We must expose whatever low power features that hardware technology gives us all along the technological stack. This is the only way in which we can achieve efficient computing in an active power budget of 1 to 10 milliwatts. So in practice, how can we do this? How can we build such an energy efficient architecture? Well, what we did was starting from a very simple, efficient in terms of area and power processor, which is based on the OpenRISC ISA and can deliver about 1 of IPC, usually. It can be implemented in 35 kilogate equivalents, and it's fairly efficient. Then we started inserting, we called, by the way, I forgot, we called this processor Orion. In Orion, we inserted some extensions which are useful in the case of applications that are used in the IoT domain, such as extensions for digital signal processing, so vectorize instructions, post increment, multiply accumulate, and so on. We added some other features which are used to maximize energy efficiency in tight loops, which are typical of the computing kernels, you know, DSP applications and IoT applications and vision applications. That is, for example, hardware loops can be used to minimize the power spent in tight loops inside kernels. We provide features for one-cycle memory access and support for unaligned accesses from our cores, because we do not want to be limited in bandwidth. And that is our very simple starting point. So it's a RISC with some DSP extensions and extensions for energy efficiency. Of course, if we want to be efficient and powerful at the same time, we must drive this core at a very low voltage, because CMOS technology is most efficient when driven near the voltage threshold. But we must replicate our structure so that we can exploit the parallelism that is typical of the algorithm used in the IoT domain. Oh, I almost forgot. Sorry, Andy. I talked about OpenRISC, but that's not the end of the story. If you see Andy's presentation just after mine, you will see that also RISC-V can be used towards the same purpose. As I was saying, if we want to be performant and efficient, we must replicate our cores and drive them at a very low power, very low voltage, so that the CMOS technology is at its most efficient point. Of course, parallelizing the cores is not the end of the story. We must be actually able to do work, make them work together, and to do this, we must share the data. We decided to share the data through a TCDM, tightly coupled data memory logarithmic interconnect, which is an IP which provides us, it's similar to a crossbar. It provides us parallel access from all the cores to several banks of memory with a very low latency and a very high bandwidth, which gives us the flexibility to develop parallel programs for our processor. Of course, cores must be feeded with instructions, and towards this end, it would be a kind of a waste dedicated instruction cache to each of those cores. So we decided, why not just put a single one, a shared one. After all, these cores are meant to execute roughly the same code. They are an accelerator meant to accelerate parallel code. So we put a shared instruction cache and a very small level 0 instruction buffer inside each core that can be used to decouple the instruction cache stage from the instruction fetch stage of the OpenRISC cores. This leads to much improved energy efficiency, because we spend much less power in fetching instructions from the higher level of memory hierarchy. The internal structure of our shared die cache is pretty complex, because but the key points are that we want the fetches to the instruction cache to be completely private, and so we provide a private cache controller for each of the cores, and that can access a shared set of tag and data memories, which are implemented on standard cell memories. In this way, it is possible to access, to have an ultra-low latency private path for tag and data read access in the instruction cache. The cache controller is very simple, because it's meant to be coupled to very simple cores, such as the Orion core and our implementation of the RISC-V core. Of course, we might even want to add some more energy efficiency to our pod. And one way to do it is to exploit hardware parallelism and hardware acceleration. So our cluster, of course, is also able to be to include hardware coprocessors, which may perform some critical operations in code in a much more energy efficient way. Two examples which are already existing of this are a vision accelerator for 2D convolutions and an accelerator for streaming encryption of data, so that we can encrypt data after it comes, so that we can stream it out of the cluster encrypted. Sorry. One other trick to lower power consumption even more is using an heterogeneous memory hierarchy, which can be done by splitting our memory banks in a section which is developed using SRAMs and a section which uses standard cell memories. Whereas SRAMs must be driven within a certain voltage range and cannot be driven as low in voltage as the normal standard cell logic can. Standard cell memories have a much higher burden in terms of area, but can be driven at much lower voltage. So we can implement a trade-off between power and area, and we have a portion of memory which can be driven at very low voltages while retaining its state. Of course, no parallel architecture is complete without some support for actual parallelism in software, and to make this possible, we added, and not only possible but efficient and fast, we added an hardware synchronization unit in the cluster, so that the cores can be easily shut down and waken up by software with hardware acceleration. This also enables accelerating common parallelism things like barriers, critical sections, and so on. To further draw power consumption down, we implemented fine-grained clock gating and body biasing in our platform, especially since most of our mainline chips are developed using the ST28nm FD-SOI technology, which permits using reverse body biasing to draw leakage power to a very low consumption state. We implemented this kind of power management technique to draw power down when not using a part of the cluster. So, for example, we can keep the state of all the cores, part of the memory, and all the rest of the platform, while just one core is running and the rest is empty. Of course, this cluster of processors cannot exist by itself, so we must also add some infrastructure to access the off-cluster memory. And that is done through a DMA controller and some it's not really visible here, an instruction bus and a cluster bus which permit to communicate with the external world and the net memory. This structure is scalable up to a certain number of processors, typically 8 or 16. After that, of course, the burden of sharing memory and cache becomes too high, and so we must think of a better way to scale this to a higher number of cores. The better way, of course, is by simply replicating this cluster structure to several clusters and connecting them through a scalable medium such as a network on chip. This network on chip that can then be connected to an external interface and to, for example, a level 3 memory. It must be noted that we also want each of these clusters to be independent from the others in terms of frequency and voltage. This is an overall view of what we mean by a PULP system. Of course, I talked a lot about architecture, but what's really interesting about this PULP project is that we also have real silicon. And in particular, we already taped out 3 chips in a 28 FDSOI. One of them is in production, the other two already came back. The fourth one will be taped out soon. We also taped out several chips in a development branch of the PULP platform. One of them is already taped out, the other will be taped out soon. And there are these other experimental tape outs already being effectuated with shared floating point units. Compare several versions of failed floating point. We have some early chips that were developed to develop the Orion core, which were implemented in UMC 180 nanometers. We have a mixed signal chip already implemented in SMIC 130 nanometers, and a new one which is being planned. And finally, we have three chips which have been taped out in ALP 180 nanometers that test several approximate computing concepts. Even if we focus, I was forgetting again on Ibani, which will be taped out very soon, next month. And it's a Global Foundries 28 nanometers chip containing a RISC-based version of PULP. Even if we focus on the mainline and development chips, we can see that several of them are already ready on the tester. Some of them are at the PULP, and the others will be soon implemented and taped out. And what's interesting to notice is that three of the chips we have taped out already will be board capable, so they will be ready to be placed on the board and used. And that's pretty exciting. While we wait for that, which is not yet ready, but will be very soon, we can use an emulator, because we also developed an FPGA emulator for PULP, which is based on a Zinc board. This version of the PULP can be implemented on a Z705 FPGA using about 45% of the available lookup tables and reaching about 50 megahertz. Of course, we are not done with this, because also the FPGA has no meaning by itself. So we also designed another board which can be plugged in to this FPGA board and contains several sensor arrays so that we can really test our IoT ideas with real ultra-low power sensors. It also hosts an STM32 low power microcontroller that can be used as a host for a PULP platform, for a PULP chip. This board will be part of the Pulpino open source release. So it's open source, it will be available for everyone to use and play with. Of course, hardware does not mean much if there is no software running on top of it. So we developed two tool chains for PULP at the moment. Both of them are based on GCC and LLVM, which are the two, of course, the two most important open source compilers available. Both compilers transparently support most of the other extensions that are available in the PULP system, such as hardware loops, post-increment, multiply accumulate, vectorization, and so on. Only a couple of instructions, such as bit counting operations, have to be supported manually through intrinsic. And all these extensions can be fine-grained disabled, so that we can perform benchmarks and see exactly what the amount of effectiveness of the new extension is. We also can also run industry standard benchmarks on our platform. These are two points in core mark that are given measured on a single Orion core. We got 2.37 core mark per megahertz with GCC and a bit less with LLVM, 2.16 with LLVM. So we are on par, roughly on par with the numbers I think that were shown before. Don't ask me. I think it activates most optimizations. But maybe we should ask German. Okay. As I said, This is a parallel platform. This is meant to run parallel software. And to efficiently code parallel software, it is much more convenient to use a programming model, an advanced programming model, and not program bare metal code. So in PULP, we support fully OpenMP version 3, which is optimized for performance and power using the hardware support from the hardware synchronizing unit that I showed before, so the event unit, and then hardware test and set facilities that are embedded inside the logarithmic interconnection. This achieves us to achieve quite fast performance on typical parallelism constructs such as parallel regions, barriers, and critical sections. We can also support higher level programming models such as OpenRISC. OpenRISC is a programming model for vision in embedded platforms, which models each application as a graph or a directed acyclic graph of kernels. And we can run this on the virtual platform simulating PULP at the moment. And we also have nice features that, for example, we can parallelize kernels internally using OpenMP, and we can automatically tile the kernels and insert DMA transfers to make them much more easier to code for the developer. Speaking of the virtual platform, of course, coding for many core systems such as PULP or multi-core systems such as PULP may not be easy, especially when it is being developed. So to provide a much easier and much faster interface to software developers, we also developed a virtual platform which simulates a full PULP cluster with an host, which is implemented as another OpenRISC core, and a level 3 memory. This is developed in C++, and we also use some Python for instantiating and configuring the platform. We can integrate many instruction set simulators. We already tried with the ORCONF and the simulator used in GDB. And support for the RISC-V instruction set simulator is ongoing. The model inside the virtual platform is event-based, so we can include timing models for many of the instances of the modules inside the platform, such as DMA controllers, for example. And the performance of the platform is around 1 million of instructions per second. This is functionally aligned with what we have in real hardware, and the timing accuracy from what we measured is within 10 to 20% of the target hardware. We also have some nice features for profiling our software. We can extract program counter traces from the R2TL and virtual platform simulations. We will also be soon able to do the same for FPGA emulation. And we can catch also several events, such as stalls or cache misses. And using the open source tool Kcache Grind, we can plot them quite nicely, as you can see. It's very powerful tool. We can also use the standard debugger GDB. This is supported currently on the RTL and virtual platform of PULP. We use a bridge to insert JTAG requests inside the RTL. And most GDB features work, such as stepping, breakpoints, introspection. We forked this from the Minson project. Before concluding, I will show you some results we got with the PULP. This is a slide about the results we got by extending the Orion core with our DSP-like extensions. So we show what happens with respect to a baseline OpenRISC ISA compliant version of Orion. If we add the first hardware loops, post-pre and post-increment, optimized multiplier accumulate operations that work directly on general purpose registers, and vector extensions. We also show the comparison with the Cortex-M4. Of course, in this case, we didn't use intrinsics in the Cortex-M4 core, so it's a bit slower than our implementation in this case. And by carefully optimizing the code, we can get up to 5x improvement in some cases using vectorization and combined with all the other improvements. In this second slide, I show a comparison on a bit more complex set of a complicated set of kernels, which also include DMA transfers and back and forth from L2. And we also in this case we observe that in most cases the Orion core can be a little faster than, or also a lot faster in some cases than Cortex M4. If we also consider, in this case, we also plot the results with our OpenMP runtime running on the real FPGA emulator of PULP. And so we can see that the overhead of parallelism is contained, and we almost always get the desired speed up. We had 4 cores in this instance of PULP, and we almost always get 4x. Or even if we get less, this is not due to our runtime, it's due to bad parallelization on our part. So, I will give some outlook and research directions for the future. First of all, we like to make bigger versions of PULP, including more than the 4 cores per cluster that we do now, and including more clusters connected by a network on chip. Furthermore, we would like to make PULP more heterogeneous. We already have done that a bit using hardware convolution engines in PULP 3, and we are also working, as I said, on streaming encryption accelerators, but we want to push this further and put more accelerators inside the PULP clusters. Of course, not in all cases we want to make huge PULPs, but we could want to make many of them and make them work together. So we're also working on multiple PULP chips that are able to work together while connected using very fast ultra-low power I/O connections. We will also work on real-time virtualization extensions for our PULP chips. And finally, another development similar to the heterogeneous PULP, we also want to extend PULP with some kind of coarse-grained reconfigurable accelerator that can be used as a more flexible accelerator, even with a small loss of energy efficiency with respect to a full custom accelerator implemented in ARM. So of course, building an ecosystem for exploration of next-gen parallel computing on silicon is not easy, so we got a lot of help from several universities, research centers, and companies. We also worked a lot. There's a lot of people already working on that. 3 professors, many postdocs, PhDs, master students, a lot of work. But we are still looking for someone which could help us, which is skilled enough and helpful enough for us. In particular, we would like help in the fields of technologies such as non-volatile memories, ultra-low voltage SRAMs, which can be competitive with what we currently do with solid memories, low power libraries and IPs, different technologies from what we already have available, and advanced packaging techs. We could also use help in RTL and architecture. We would especially like memory interface, very fast memory interface IPs, if you got some, please tell us. On chip voltage converters, CAG arrays, as I mentioned. Design automation such as advanced verification techniques, testing, self-testing, and support for technologies such as ETHZ for building platforms in a semi-automatic fashion. And software support, especially for new compilers based on UCC, operating system supporting, such as FreeRTOS. There is one of us which is already porting FreeRTOS on PULP, parallel programming models. I thank you a lot for the attention. If there are any questions, I will be happy to answer them. And don't forget to watch Andy's presentation. End-to-end. I personally, or in general as a group? Okay. such as especially images, in such a way that we can produce concrete features out of them. So let's say extract high-level features out of an ULP imager and use them. We already have some of it. We do not have a full system anymore, but we have most of the parts.
I have a question. You mentioned something about kind of low power standby kind of track biasing in the body.
Yes.
And other low power techniques. So, I mean, from the slide at 65 nanometer, it looked like you were, for a single core, you were about the same, maybe a bit worse than the other core. Is that right?
Oh, yeah, I should check.
But
the first numbers I mentioned during the presentation, during the architectural presentation, mainly referred to 28 PSI. So our back body biasing techniques are mainly thought for the FDSI technology. As I said, the point is that you must expose low-level technology, low-power features all along the technological stack. So for our exploration, we also used many other kinds of technologies, as I've shown us, but most of the very deeply low-power techniques are thought on the 28 FDSI.
sure. And so, where do you think you've actually made a major win in terms of some sort of implementable?
In the architecture, I mean, or in the technology?
Overall, yeah.
Overall, I think the shared die cache is pretty much a big win because it saves most power. 30% of power. In the first version of PULP, we had private instruction caches, and the improvement is very substantial, like 30%.
You look like you're doing something copying with your voltage domains.
Okay, of course we also do a lot of clock gating, but that's normal.
Sure.
Every design does that. There's nothing new.
So compared to sort of other perhaps IoT chips that are available commercially, have you compared yourself for a particular application, or are you benchmarking against that sort of stuff?
We benchmarked against microcontrollers mainly, which work in the same power range, so below 10 milliwatts. That's the point. Because we want to be able to do more complicated applications in the same power domain, in the same power envelope.
Since this is an open hardware conference,
Yes.
I'll ask about open aspect of the project. You mentioned the open acquisition. You're making use of some of the open source works, but what about the rest? Is a substantial project, multiple tapeouts, complicated hardware parts, frequency components, and so on and so forth?
I think this answer is better suited for the next presentation, which we've talked a lot about that. But okay, here I present the whole project. Not all of the whole project will be made open source at the same time because it's very complicated. So, but a big part of it will be very soon made open source. But I will not spoil it. Full ending.
Thank you very much, Francesco.